Please do. I'm just talking here only a little to bridge the gap. We are moving into some completely different environment, and it's looking at structures under corrosion. And this is our colleagues from, it's called the Armor Lab, where you could certainly use that one for arms, but you could also use it for a variety of other environments where it corrodes. They are going to show us, they are from the University of California in San Diego, and they're going to show us a system that enables a non-contact and subsurface damage quantification localization. And it's basically like computed tomography, which they are showing here, but the details of the technique will now just be presented. They will also show that one you have over here, the tomograph. I guess Tony is instructed what he has to film now and to show. And that's, I think, mainly what had to be said here. Oh, there's already the slides, so maybe you can give it a start.
Do you want to give it to me? All right. So should I tell them to switch when I want it to be switched? It's okay, I'll All right, good afternoon. My name's and this is my PhD student Sumit Gupta, and we're from the Armor Lab at UC San Diego. Today I'd like to just present to you some of the recent work that we're looking at in developing a non-invasive and non-contact subsurface damage detection system that hopefully in the near future could be made into a portable system to scan structural components and different materials. Now, for the system that we're showcasing today, there's essentially three main parts to it. First is the hardware system, as you'll see very soon after we switch to video, on my left here. The second part is the computational engine, if you will, the algorithm and the measurement strategy that takes the raw data that we're collecting to obtain these cross-sectional images of materials and components. And lastly, to enable the selective detection of different stimuli applied to the material or different forms of damage, we're embedding different materials that also act as sensors within these materials, or they could be painted on the surface, like you see on the right over there. Now, the potential applications would be, detecting corrosion in cables, or corrosion in reinforced concrete structures, or even measuring strain, or in the case of the work that we're doing for ONR and looking at biomedical applications. Now, can we switch to video? Yeah. So Sumit right here is going to show you the hardware system. So if you could, I can't really see the video actually. Right, so this is the measurement array. So essentially it consists of a bunch of electrical plates embedded in this cylinder component. This is larger than it needs to be because it's actually more sophisticated than what we need for here today. But essentially the commercial data acquisition system here allows us to inject an electric field and propagate it through the space. And while the system takes high sampling rate capacitance data. So Sumit here is going to show you a pristine metal rod inserted into the space. Now, before we started this, we've calibrated the system, so you're not supposed to see anything. Just a slight change due to the presence of that object. And then, so you could take that one out. And our goal here is to try to detect corrosion. So this is just a steel rod that's been corroded, and there's no coating applied to it. So again, the point here is that because even though we have rust developing on the surface of these metals, the material properties don't change tremendously. So if we're just using this sort of imaging technique, we might not see a lot of change, if you will, in the images. So in the last part, we have a metal rod that's been pre-coated with this conductive polymer and nanocomposite coating. So and that's been corroded for some time. So he'll insert that. And what you can see is a slightly more significant change, indicating that we could combine the imaging technique with the thin film coating to detect those changes. Now, can we switch back to the presentation really quickly? Now, unfortunately, our concrete specimens did not survive TSA, but fortunately we have some slides here. Essentially, we don't have to necessarily just image the steel itself. So these are actually reinforced concrete cylinders with a metal rod embedded inside of it. We can use that same scanning system to essentially generate these cross-sectional images as we run accelerated corrosion tests. And you can see from those just a color change as an indicator of corrosion developing in the material. Now, if we switch back to the camera again, just to showcase the technique, Sumit here is just going to quickly validate this. So he has a rod just to show you that the algorithm and the technique is capable of detecting these objects in real time. So he'll start that up. So you can see that tracking of that green dot. And then to better showcase so the second rod that he has on him is actually been pre-coated with this same polyaniline thin film, conductive polymer thin film that's sensitive to pH as an indicator of corrosion. And that's been exposed from pH 1 to pH 13 at 4 different locations. So he's going to slowly insert that rod. Go ahead. And then, so this is a pH 1, should be just a light color, and as he continues to expose to image higher pH levels, that image would get more and more severe, or the color change is more extreme. So that's just, I believe, 1, 5, 9, and pH 13. Okay. And then if we could switch back to the slide real quick. So the computational engine right here is using a lower resolution algorithm, if you will. But if you have some time to spare, we could actually run this iterative process to generate higher resolution images, such as the one shown here. And this just shows you 6 examples that you can get with this technique. So Sumit has so right now, our last quick demo right here involves using a slightly different sensor array that looks like a pipe bomb. Maybe I shouldn't say that, actually. But what we want to show you is that by changing how we design these films and how we're coating them onto different structural components, we can measure different stimuli. So we showed you the detection of pH, and now the next demo will show you how to measure a strain. So can you zoom in on this real quick? So to facilitate this demo, we found some essentially very flexible rubber hose, if you will. So this is a pristine rubber hose, and Sumit will show you that when he inserts it into the sensing array and he'll try to stretch it by hand, you won't see much of it. But we've also had an identical rubber hose that we've pre-coated it with a carbon nanotube-based thin film, and that's been patterned on the surface of this coating to enable us to detect strain. No, we'll do the demo first. So yeah, the challenge here is he has to unplug 16 cables and plug in 16 new cables, all in the right order. Little does he know that this is his second qualifying exam. Yeah. Okay, so I guess as Sumit's setting that up, maybe we could switch back to the slide. I'll show the results real quick from what we could get, and then he could show the live demo. So essentially, working with Lintrix and my colleague Michael Todd with their load frame, we've been able to take these rods and essentially apply compression to them. So you can see that, again, this is non-contact, right, with the rod being imaged using the hardware system. So as we apply greater compression, the color of those maps change, indicating the level of strain we're applying to the system. One of the nice things about the load frame is that it's easily configurable. So instead of applying uniaxial load, we could also swing that end arm, and it's actually on a pivot, and conduct a test similar to a cantilever beam test. So these are just another set of results where you can see that as we apply greater out-of-plane deflection, you know that for a simple beam, there's a compression face and a tensile face, and that change in permittivity is what we're measuring. So you can see the development of those compressive and tensile faces. So I think now Sumit should be about ready. We could switch back to the live video. Oh, sorry. Right here. Okay, so he's going to first insert the pristine rubber hose, so nothing, no coating, nothing into the sensing array. So what you should see after he threads it through is just a colored dot indicating the presence of that hose, and you can stretch it, but essentially you don't see much change, right? Okay, so now if we switch over to the coated hose, you'll make a very good magician, by the way. I like how you display it. Yeah, yeah. So as he stretches it, you can see that the color changes more drastically if he's not shaking too much. Right. So essentially, yeah, you can sort of see that change. Yep. All right. I think that's about it. Thank you very much for your attention.
Thank you very much.